Welcome back to the MVPN video series. In today's video, we discuss the need and effect of using Source Specific Multicast or SSM in the provider core for the MDT GRE. We will begin by discussing some consequences of using ASM groups or any source multicast groups for the default MDT. Then we will discuss the set of requirements that need to be satisfied in order to use SSM groups. And finally, we deliver a demonstration where we replace the previously configured ASM group with an SSM group. So let's begin. Now, ASM-based default MDT GRE, so Rosen GRE that we built based on an ASM group. What are some of the consequences of using ASM? Well, there are some pros and obviously there are some cons. First, let's go through the pros. So there is no external signaling needed. All you really need is the CPIM overlay between the PEs. That means you're running no other protocol. Well, you're running PPIM to sort of create the trees. But other than PPIM or CPIM, there is no other protocol. So you're only dealing with multicast protocols, PIM. Now, this is because the PEs only need the provider group addresses. That PG or provider group address is the destination address of the MP-GRE tunnel. So that's all the PEs need. They will start sending data on it, and they will join a star comma G tree for that group. And where do you send the joins for the star comma G tree? Well, that's right. You send them to the RP. So the RP information is always disseminated somehow in a multicast network, so that's the only information you need. Each one of the PEs will then connect itself on a star comma G tree to the RP, so they will join that leg of the tree, and they will also register messages to the RP. This is the unicast registering process. It is up to the RP then to connect the two trees together. So those are the nitty-gritty details of multicast. But essentially, if you understand multicast, you understand how the RP can then connect the two trees. Once the two trees are connected, the data starts flowing down the star comma G tree for each and every one of the PEs. They will learn about what other sources exist in this particular network. So namely, those sources are going to be the other PEs. So you're essentially learning about your S information, the P source information, in the data plane. And once you know that information, usually all of the PEs or all of the receivers will then switch over to the shortest path tree. So they then create, using an S comma G join, a tree right to the source, and that is the shortest path tree. So those are all of the pros. Then what are the cons? Well, cons, the heavy con here is the amount of multicast state that you have to maintain on the provider routers. PIM is a soft state protocol. That means every 30 seconds or a minute or whatever have you, you are refreshing the information. There is no acknowledgement. So it works sort of like UDP, and you have to keep refreshing over and over and over again. So the more state you have, the more messages that you need to maintain that state, the more data in the control plane that you need. In this case, you have to maintain the star comma G state. Even though you have moved to the S comma G using the SPT switchover, you need to maintain the star comma G state between yourself as a receiver and the RP, just in case there are new PEs that join that group. So you still need the data from a PE you don't know yet about, and therefore you need the star comma G tree. The consequence of this is going to be that every single provider router that exists between a PE router and a P router, well, load balancing aside, but roughly every P router that sits in the path between the rendezvous point tree, so the RP and the receiver, will have to maintain the star comma G state and will have to be refreshed. And every single router that is between two PEs. So again, shortest load balancing aside, almost every router that sits on that shortest path tree between every single pair of PEs would also have to have the S comma G state, because that's how the joins are working there. So now that is a lot of state to maintain. So star comma G states and S comma G states both have to be maintained, and there's a good reason for it. You can use PIM-BIDR. PIM-BIDR is an option. It shouldn't really be in the con. It could be somewhere in the middle. It will reduce state. So PIM-BIDR does not necessitate the maintenance of the S, G state, since everybody is on A star, G. And the default MDT especially is really good for PIM-BIDR, but at the same time, you may not get the shortest paths. So between two PE routers, you would always have to go through the rendezvous point, because that's how PIM bidirectional works. So there is a reduction in state, but then you lose your shortest path. So what is the result of this? Well, the result is we should look at SSM or Source Specific Multicast based default MDT GREs. So what are the pros of this? Again, there are going to be pros and there's going to be cons. The pro is you will reduce multicast state in the core, but not like PIM-BIDR by sacrificing shortest path trees. You are sacrificing the other end of it. So you're sacrificing the star, G tree, and you're maintaining only the S, G state. So that's sort of a win-win, because you get the shortest path tree and you also get to maintain only one state. Furthermore, you don't need any RPs. So the RPs are gone away. But now let's move into the con. The RP going away actually is a big con, because remember, the RPs used to bring all of the sources and receivers together. Well, there are no RPs left anymore, so how do you go and join the S, G tree? Because previously with ASM, you were learning about the sources in the data plane. Well, that's out of the question now, because there is no data and it's a chicken and an egg problem. But the PEs need to know about other MVP and PEs, and if you start configuring them, that's going to be a big problem too. So there's no RPs, and configuration is kind of a big hassle. Well, if only there was another way of learning this. So if there was an out-of-band method somewhere outside of the data plane, outside of PIM, where PEs could share their S, G information with each other, well, wouldn't that be splendid? Well, as it happens, there is such a method. In comes BGP SAFI Subsequent Address Family Identifier 66, or also known as the BGP MDT. And this is again in the Draft-Rosen RFC. So this was defined for this specific purpose in the Draft-Rosen RFC. It's AFI1 SAFI 66. And the NLRI in this BGP advertisement contains three specific pieces of information. The first piece is route distinguisher. That is outside the scope of our current video series, because that is for inter-AS multicast. It may be covered in a later video, I don't know, but for this particular video, since we are doing intra-AS, we are not going to worry about the route distinguisher. But the other two things are absolutely important. The second thing, or the second piece of information here, is the PE's IPv4 address. So each and every one of the PEs are going to share their IPv4 addresses in this SAFI. Along with that IPv4 address, they're also going to share the MDT group that they're willing to receive the traffic on. And bingo, once these families are exchanged and the advertisements are exchanged between PEs, now they know that S, G information that they were missing before. So all PEs in the VPN, in the MVPN actually, will become BGP MDT neighbors. They will then exchange the S, G information, and from this point on, they can use that information, just like normal, to build shortest path trees to each other, or SSM, Source Specific Multicast trees to each other. So the part that was played by the rendezvous point is now being played by BGP. Well, all that is well and good. What we are going to do now is going to be much more fun, because we will take this concept and actually implement it on our currently working ASM network. So we'll remove the ASM configuration and we'll put in this SSM configuration and see how many other pieces of information need to be configured. So just to recap, this is the same topology with the routers in the same condition as we left them at the end of video 2, which was MDT GRE working on PIM ASM. So if we go to our core routers, and let's take a look at router 1 first of all, and if I say do show IP mroute, I will see that we are still forming a star comma G tree to 239.123. That was our MDT group. I also have three S comma G trees, one for XR1, one for R4, and then one from this router that the other routers have joined. Now in this case, our RP is R3. So do show IP PIM RP mapping. And let's take a look real quick at the router that is farthest away from R3. So XR1 seems to be that router. And let's take a look at XR1 and how its star comma G tree works. So show PIM topology 239.123. And the upstream interface here is the local interface 521, and the upstream neighbor is R5. So it goes directly to R5. So let's go over to R5. And on R5, we will see do show IP mroute 239.1.2.3. It also has that star comma G state. The RPF interface is 35. That's the interface between R3 and R5. And then the neighbor is R3, and then R3 finally would have that tree, probably with about 3 interfaces in the oil. It could be up to 2, but could be 3. So do show IP mroute 239.1.2.3. So there are those 3 interfaces in the oil for 239. It also seems everybody has registered to it, so it's also going to maintain the state for every S comma G because of the initial registration. So whether the shortest tree passes through there or not, it's at least going to have the initial registration. So there is a lot of state all across our network. Now we are going to change this with PIM SSM. And the very first thing we're going to do then with PIM SSM is to make sure that all of the core routers, that is R1 to R5 plus XR1, all understand PIM SSM and they can process PIM SSM. They do not do this by default. So the command for that then on iOS routers is ipPIM SSM. And then you can either use the keyword default, which then uses the group 232/8, 232.0.0.0, whatever number of addresses to the power 24 that are in there for SSM. Or you could use an ACL to define a range. Once again, I've said this is not a multicast lab, so I'll just go with default. And what that then means is that the entire group 232/8 is now being treated as an SSM group. It wasn't previously. That is going to have to be done on all of the iOS routers. So yeah, I'm going to not go into the config mode of XR yet. And I'm in the config mode of all of the iOS routers. So I'll, again, cheat my way through it. I will say ipPIM SSM default. And now we should have SSM enabled on all of the iOS routers. The good news on XR is that it already treats that group by default as an SSM group. And the proof would be in your show PIM topology. So if you'd say, no, not show PIM topology, show IP, show PIM range list. So that was the good command to use for your RP mappings, but it also shows you that SSM is being treated. 232.0.0.0/8 is being treated as SSM, so there is really no further configuration necessary on this. The next thing then what we have to do is we have to change the MDT group to something SSM. So in this case, I'm going to change it to 232.123, carrying on with the same 123 theme. So remember where we did the MDT config? That was in the VRF itself. And in the VRF, under the address family IPv4, you declare the MDT. Now you don't have to make any changes other than just define the group. So as long as the group defined is covered by that SSM default command, the local router then treats it as an SSM group. So let's begin with router 1. So VRF definition C1, address family IPv4, and then MDT default. And as you can see here, it doesn't really care which sort of group it is. The router's multicast protocol defines that. So 232.1.2.3. And I would have to deconfigure this earlier MDT. So a new tunnel ID, that's okay. So that I'm not too worried about. I'll take this MDT default and put this back in here. I'm going to quickly configure this on R4 as well. And I'll copy the history from here, and it will be all of these commands that have to go on R4 as well. Okay, and finally on XR1, this was not under the VRF, this was under the multicast routing. Under the VRF, under multicast routing. So we'll go inside this VRF, inside address family IPv4, and I'm going to deconfigure this other group, no longer needed, and we'll say MDT default IPv4 232.1.2.3. Commit this config in. Now, one more thing that I'm going to do here is I'll also clear the multicast routing table. So do clear IP mroute, and I'll specifically just clear the 123. It's not going to work on XR. And on XR, I frankly don't remember the command. Let's try clear PIM topology. And now I can say 239.1.2.3. So now, on these routers, let's try do show IP on the iOS routers. Let's see do show IP mroute. And you can see that they have not really done anything yet. So on R1, which should really be treating that group as an SSM group, it really hasn't done anything yet. And the main reason for that is the lack of the BGP MDT family. So it knows it cannot really do anything without providing that information to its neighbors, without receiving that information from its neighbors. And for confirmation's sake, let's also confirm it on the other PE, which is R4. So we'll say do show IP mroute 232.1.2.3. And that group is not found here. The multicast routing table just has that auto RP group that remains there by default. How about XR1? Sometimes they behave a little bit differently. So do show PIM topology, and this would be 232.1.2.3. And that, like I said, they do behave a little bit differently. That at the very least has created the S, G tree. But there is no forwarding going on there right now because nobody knows to join this group yet. So they are unaware of each other's inclination to join the MVPN. The next thing here then is to start that address family, the address family MDT, and then become neighbors on that. So let's look at the BGP currently. Do show run section R BGP. And what I would have to do is take this address family VPN v4 and do the exact same thing for address family IPv4 MDT. So I'll copy that. I'll say router BGP 100, address family IPv4 unicast MDT or IPv4 MDT. So that's the multicast distribution tree family. I've already copied all of this, so I'll put this back in. Actually, the extended community is not needed in this family. It used to be needed before the family was completely defined in the RFC. So some of the older routers may need it, but once the SAFI was defined, you don't really need to send the extended community there because there is no concept of route target or anything like that. Let's do the same thing on R4. Do show run section R BGP, router BGP 100, address family IPv4 MDT, and then I will activate this neighbor and then activate that neighbor. So R1 seems to be happy with R4, R4 seems to be happy with R1, and 21 is not happy with either one of them. So let's take a look at how we can fix our XR1 and show run router BGP. And this is going to go under the neighbor family here, and you would also have to activate the address family itself. So let's go ahead and do that. We'll say router BGP 100, address family IPv4 MDT, and under each one of the neighbors, address family IPv4 MDT. So there we go, that is committed. Hopefully on R1 and R4 we start seeing BGP come up as a neighbor. But right now R1 and R4 are definitely neighbors, and we can confirm that by saying do show BGP IPv4 MDT all summary. And in fact both of them are now up. We are also receiving a prefix from R4, and so far I'm not receiving a prefix from XR1 yet, so we'll have to see what's going on there. But at least from R4 I am receiving a prefix. Let's take a look at that prefix. So we will say do show BGP IPv4 MDT all, and there's one route that I'm receiving, and it is the loopback for R4, so that's my S. And let's take a look inside that route, MDT all 4444. And here I can see that I have the S from here, and then my MDT group address is here. There is also a an RD define, which is this 4444 colon 100, but the rest of the information is what matters. The MDT group address and the address for the router itself, which is 4444. So now what we should see here then is R1 and R4 should start building those trees to each other. So let's take a look at that. Do show IP mroute. And they indeed are building those trees to each other. So R1 is definitely building a tree towards 4.4.4.4. And it just became adjacent. Actually, it looks like it just became adjacent with 2121, so the prefixes may have come in. But somebody is building the tree to myself as well, so I have my own S-G. Let's take a look at this again. And this time I have all three of the S-G states. So whatever was the delay with BGP, it seems to have resolved itself. And now I'm getting a prefix assigned. And once I get that prefix assigned, the same exact sequence can happen. So the rest of the show is exactly the same as PIM ASM, but now it just happens to be working on PIM SSM. Let's take a look at XR1 as well. Do show PIM topology. And as you can see, it also has all of those, all of the S-G states, the three that we need. Now, R3 used to be RP, and it had a whole bunch of state on it, as you can see. What is the state on it now? Let's see that. Do show IP mroute. And I think it happens to be on the shortest path tree for everybody, unfortunately. But that's why it's keeping all of that state, but it still doesn't have the star-G state with the big oil. But let's take a look at a router that is completely outside that dimension. Let's take a look at R2. do show IP mroute, and that really literally has no state on it. For a router like R5, I would probably expect 1 or 2 states on it. And again, this is all due to how the shortest path first is working on this, or I'm sorry, the shortest path 3, the load balancing is working, because there's a whole bunch of ECMP in this topology. So PIM doesn't really load balance. It uses the highest or the lowest IP. I forget which one, but if it has 2 RPF IPs, it'll pick the higher or the lower. That's how it breaks the ties. So do show IP mroute on R5. And that still has the 2 states on it. So R4 and XR1 are both going through. Actually, no, both of those states, this state is to connect R1 over to XR1, and then this state is to connect XR1 over to R1. So it still doesn't have the state for R4, but the bigger the network, the more benefit you would derive out of this. And finally, let's see if everything else in the customer, on the customer routers is working. So the way we did that last time, I think, was go on R9 and go on R10 and look for RP information, right? So show IP PIM RP mapping. And there we go. The RP mapping seems to be good. Let's take a look at R10. Do show IP PIM RP mapping. And that is good as well. And R6 should be, there was a group that was joined on here. Let's take a look at that. Do show IP IGMP groups. And what R10 had done was join the group 239.111, and we should be able to ping it from R9. And let's really quickly try to do that. Ping 239.111, or is it 111 or 123? 111. And we will ping it from the source address of loopback 0, and we'll repeat about 10 times. And we'll try to see if that actually works, which it is. So the multicast core is working exactly the same way, but with a lot less state. So there is no star comma G state right now in our core at all. Now, before I leave you, there is one more command that you would want to see, and this is more for troubleshooting purposes. And the command is show IP PIM VRF. So this would be inside the VRF MDT BGP. And that will actually show you the received states, the received S comma Gs that you have for any group, 232.123, because remember, it's the group, not the RD. It's the group that the router uses to determine which particular MVPN these advertisements are for. And in this particular case, the advertisements are for 232.123, so it's all well and good. Well, that's it for this video. In our next video, we'll further optimize the SP core by implementing on-demand trees, which are called data MDTs. These are beneficial for your high-volume multicast traffic. But for now, I hope you've enjoyed this video, and I will see you again real soon. Thanks.